Okay, moving onwards, this is the next problem, which says that a flat plate of width 1 meter. So this is not the width, it is the length. The length that we see over here is the length and not the width. Width is going inside the computer, inside the system, or inside the board. Is maintained at a uniform temperature of 230 degrees Celsius. So it is a constant temperature problem. Ts is constant. It is not a constant heat flux problem. So it is maintained at a uniform temperature of 230 degrees Celsius by using independently controlled electrical heaters. So these are various heaters that I have put in series, each of which is 50 millimeters long. So each has a length of 50 millimeters. Now if the atmospheric air at 25 degrees Celsius, we are given T infinity. So it is air which is flowing over this plate at 25 degrees Celsius, flows over the plate at a velocity of 60 meters per second, U infinity. At what heater is the electrical input a maximum, and what is the value of this input? At what heater is the electrical input a maximum? So which heater would have maximum electrical energy or power input? So we have to find out Q max, and we have to find out at which heater maximum Q would be taking place, maximum heat transfer would be taking place. Now after evaluating the properties at the mean film temperature, which is the average of Ts and T infinity, 400.5 Kelvin, so you may approximate it as 400 Kelvin. We now need to see where would maximum heat transfer occur. Now maximum heat transfer will occur, you may say, wherever there is maximum value of H. And if you take a look at this diagram again, maximum value of H would occur over the first heater if and only if the flow is entirely laminar or entirely turbulent. Because if the flow is entirely laminar or entirely turbulent, there would not be this transition, and it would be either this decrease taking place all over the length of the plate, or it would be this decrease taking place over the entire length. So therefore, where would maximum value of H be? It would be on the very first heater. So therefore H would have its maximum value on the first heater if and only if the flow is entirely laminar or entirely turbulent, and therefore Q would be maximum over the first heater. So we need to find out whether the flow is entirely laminar or turbulent, or it is not the case. So if we calculate that Reynolds number, and if we put that value of Reynolds number as 5 exponent 5 in order to find out this critical length, right? This critical length. So since we have put Reynolds number as 5 exponent 5, so that would occur where x is x critical. So we get x critical as 0.22 meters, means 220 millimeters. So each of those heaters is 50 millimeters long. So 50, first 50, second 50, third 50, and then fourth 50. So fourth 50 would make it 200 millimeters, and then the fifth 50 would make it 250 millimeters. So where is the transition taking place? Transition is taking place over the fifth heater, right? Now this is what I have written over here. So the maximum heat transfer may occur either on the first heater if the condition exists that I have just discussed, or it would be on the fifth heater if the flow is changing from laminar to turbulent through that transition period. And in addition, it is mentioned over here that the maximum heat transfer may also occur over sixth heater. So why sixth heater? Because fifth heater is quite understandable, because if the transition is taking place over here on the fifth heater, if the transition is taking place over here on the fifth heater, first of all we will say that it is taking place abruptly as discussed before. So then how the maximum heat transfer will be taking place from the sixth heater? See, there is a reason behind that. When we talk about the fifth heater, if we talk about the fifth heater, these are the values of H. These are the values of H that we are getting from the fifth heater. And all those different values of H will result in different values of local Q, and therefore the average H would be H bar and the average Q would be average Q. So we will get an average Q, and that average Q would be due to average H bar, and that average H bar would be the average of all those values in this box. Now in this box there is an increasing trend and there is a declining trend. This is very important. You need to understand that in this particular box, which corresponds to the fifth heater, there are some smaller values which are increasing to the highest value, and then there is a decline. Now if we try to make the same box on heater number 6, we do not have an increasing trend and a declining trend. Rather we have a declining trend only. So if on fifth heater, if we do not have it, but suppose that if on the fifth heater we had a declining trend which would have continued over the sixth heater, we could have said with 100% surety that heat transfer from the fifth heater would be greater than the heat transfer from the entire sixth heater. But what is happening over here is that on the fifth heater there is an increasing trend and the values of H are increasing from lower values to this highest value, and then there is again a decline. So we cannot say with 100% surety that whether Q would be maximum from this plate over which the transition is taking place, means the fifth heater. Again I repeat that point, and that is important. Let's say we talk about 6 and 7. This is the 7th heater, right? Let's say we compare 6 and 7. So what would be happening on the 7th heater? This is the average H, means these are all the individual values of H, and we will get the average H from all those values of H. Now if I ask you a question that would the average H be more on 6 or on 7? If the average value of H be greater on 6 or 7, what would your answer be? Your answer would certainly be that value of H, value of the average H would be more on 6. Why? Because on 6 we have got all the values of H which are greater than all the values of H on 7. So therefore average convective coefficient, average H on 6 would be greater than average H on 7. Therefore average heat transfer from 6 would be greater than average heat transfer on 7. But it is not happening on 5 and 6, because there are some smaller values of H and which are increasing to a higher value, and then there is a decline again. So we need to find out whether the average H over this entire plate 5 is less than the average H over this entire plate 6. Means ultimately we need to find out whether Q from 5 is less than the Q from entire 6 or not. So that is why it says over here that we need to check both the heaters 5 and 6 to find out the maximum heat transfer, in addition to finding out the heat transfer from the first heater. So let's say if we say that if we start for heater number 1, we find out the Reynolds number, and it is 1.1 exponent 5. Again, it is the flow is laminar, and we use this expression for average Nusselt number. So we get the average Nusselt number over the first heater, right? Over the first heater as 197.7, and upon evaluating it to equating it to H L over K, where H would be H bar, we get H bar means average H over the first heater. Average H over the first heater as 133 watts per meter square Kelvin, and therefore we get the Q from heater 1 as 1370 watts. Now when we come on to the fifth heater, we would be evaluating the heat transfer from the first heater in this manner, and I hope that it would not be difficult for you to understand that the Q from the first heater would be the difference between the Q from the fifth heater would be the difference between the Q till fifth heater minus the Q till fourth heater. Because when we apply those expressions would give us the values of H bar, for example, starting from the start of the plate till a particular value. Now you should recall that problem in which we had calculated the heat transfer from the first 35 centimeters. That there is a particular reason for that problem. So we would be able to find out the value of H bar or value of Q from the first X centimeters or from first X meters. So we can start from the start of the plate. We should start right from the beginning of the plate. We cannot start from anywhere in the middle. So therefore Q5 would be Q1 to 5 first heater to fifth heater minus Q1 to 4 first 5 heaters. Q1 to 5 means the heat transfer from the first 5 heaters 1, 2, 3, 4 and 5, and this Q1 to 4 refers to the heat transfer from the first 4 heaters 1, 2, 3 and 4. So how do we find out the heat transfer only from the fifth heater? Just take the difference between the two. Now for Q1 to 4, again we would be calculating the Reynolds number. Kindly note that the length would vary. It would be 200 centimeters. For the first 4 heaters, the length would be 200 centimeters. So we get this value as a 4.5 exponent 5, which is less than 5 exponent 5. Therefore the flow would be considered as laminar. So we will use this expression of average Nusselt number. Why? Because we are trying to evaluate the Q from the first whole 4 heaters. So therefore Nusselt number would be averaged Nusselt number, and heat transfer coefficient would be the average heat transfer coefficient over the first 4 heaters. Therefore Nusselt number would come out to be 395.5, and upon equating it to HL over K, we get H bar as 66.8. Now this value of H bar is the value of the average coefficient over the first, second, third and fourth plates. And if you compare it with this value of H bar, which was 133.6, if you compare it with this value, if you compare this 66 with this value of H bar, which is 133, see why we see the difference. This is the average convection coefficient over the first plate only, and while the same laminar flow is continuing on the second heater, the third heater and the fourth heater, so H would continuously be on a decline. So on the second heater, the third heater and the fourth heater, the value of Hx would continuously be declining, would continuously be decreasing. So when the value of average over the first 4 plates will be calculated, it would have a lot of values that would be very less, thereby giving us or yielding the value of H bar as 66, which is less than 133. And upon putting it in H bar Ts minus T infinity, we get Q from 1 to 4 as 2740.4 watts. So from the first heater it was 1370, but the first and the second and the third and the fourth heater combined are giving us 2740 watts. Now all we need to do is find out Q1 to 5 in the same manner and take the difference between the two. So 1 to 5 is the mixed flow due to transition, because we have already calculated, we have already found out that the transition takes place at 22.22 meters, 220 millimeters, means the fifth plate. So on the fifth plate it would be mixed flow, right? So therefore the flow will be considered as mixed over the heater from the beginning till the fifth heater, means from the beginning till 250 centimeters. Till 250 centimeters the flow is not only laminar, so therefore it would be considered as mixed. And for mixed flow, this is the expression of the Nusselt number. If you go to those previous slides that we have discussed, I think it was probably the fourth or the fifth slide in this particular chapter number 7. So we had first the slide over the for the flow over a flat plate when the flow was entirely laminar, and then entirely turbulent, and then mixed. So this is the mixed case. So when we put in the values, we get the Nusselt number as 542, and this is the Nusselt number over, this is average Nusselt number over the first 5 plates. Over the first 5 plates, 1 plus 2 plus 3 plus 4 plus 5 averaged. And again, upon equating it to H bar times L over K, where L would now be 250. Kindly note that while calculating the Reynolds number, we have put length as 250, because now we are trying to find out Q and of course the Reynolds number for the first 5 heaters. So for the first 5 heaters, the length from the beginning of the plate would be 250 centimeters. Or rather, not centimeters, rather millimeters. So kindly correct all those values as exponent minus 3, because it is in millimeters. Or I can do it right over here. The values have been correctly calculated. However, so therefore, so the values have been correctly calculated, so therefore we get H bar as 73. So after putting it in HA delta T, we get the Q from the first 5 heaters as 3758 watts. Means 1 plus 2 plus 3 plus 4 plus 5 heaters are giving us 3758 watts. So Q for only the fifth heater, only, would be the difference between these two as just discussed, which would be 1017 watts. So this is the heat transfer from the fifth heater. Now for the reason discussed before, we will also find out Q from the sixth heater. And using the same thing, because when we talk about the sixth heater, so Q from the sixth heater would be the difference between these two Qs from 1 to 6, or till sixth heater minus the heat transfer till fifth heater. So we get the Reynolds number as, again kindly correct it as 300 millimeters. So this would be 300 millimeters. So we get Reynolds number as 6.8 exponent 5. Of course it shows that it is greater than 5 exponent 15. So we will be using the mixed flow and not the turbulent flow, because it is not turbulent flow over the entire plate. When we talk about the entire plate means from 1 to 6. It is not turbulent over 1 to 6. Rather from 1 to 6 it is laminar, and then after transition it became turbulent. So therefore the flow over the 300 millimeter length would be considered as mixed. So we get average Nusselt number as 748, and then upon equating it to HL over K, again it is 300 millimeters. We get average value of H bar as 84.3. right? So now what was h bar over there in the previous case? It was 73. See, it has increased. It has increased due to this thing, right? And if we then put it over here, we get the heat transfer from the first 6 heaters as 5185 watts, and upon taking the difference as discussed over here in the beginning, we get the heat transfer from the 6 heater as 1427 watts. It means those smaller values, it means that those smaller values of H are in fact reducing the overall heat transfer from that fifth plate, and they are more in the sixth plate. The values of Hx are more in the sixth plate, therefore H bar from the sixth plate is more, and therefore the Q from the sixth plate is more as well. Let's take the last problem. It says two rooms are arranged on the side of a building as shown over here in the diagram. The wall of room A is 13 meters long. So the wall of room A has a length of 13 meters and 3.5 meter high. So this height would be 3.5 meters. While that of room B is 7 meters long and 3.5 meters high. Both walls have a thickness of 0.25 meters and both have thermal conductivity of 1 watts per meter Kelvin, which is the typical value of the thermal conductivity of that material that the walls are usually made of. The following are also known. And what is that? Hi bar. Hi bar means H inside room A and room B is 5 watts per meter square Kelvin. Temperature of the TF is 20 degree Celsius. So the temperature inside the rooms, both rooms A and B, is given to us as 20 degrees Celsius. T infinity naught, TF outside is minus 20 degrees Celsius. So the temperature outside the rooms is minus 20 and inside the rooms is plus 20. And U infinity is 7 meters per second. So U infinity would be the velocity of the air which is flowing over the walls of both the rooms, having lengths of 13 meter and 7 meter respectively. Estimate the rate at which the heat is lost from the 13 meter long and 7 meter long walls. So we have to find out the rate of heat loss, because inside the temperature is plus 20 and outside temperature is minus 20 degrees Celsius. So the heat will flow from inside the rooms to outside the rooms from those walls, which have lengths of 13 meter and 7 meter respectively for A and B. Turbulent boundary layer conditions may be assumed over the entire wall. So we would be using the expressions of Nusselt number corresponding to turbulent boundary layer over the entire surface, over the entire plate, because this would be considered as a plate. Now this is the data that is given. Delta X thickness of the wall, thermal conductivities of the walls of the wall material. So we have to find out QA and QB. Now if we use this simple expression, because we know the temperature inside, we know the temperature inside the room. Over here it is plus 20 degrees Celsius. So it is plus 20 degree Celsius, and we know the temperature outside, which is minus 20 degrees Celsius, and in between there are of course three resistances. One is the convective resistance between the inner air and the inner wall, and then there would be a conductive resistance in Cartesian coordinates through the thickness of this wall, and then there would again be convective resistance between the outer wall and the atmospheric or ambient air. So there would be 1 over HA, there would be delta X over KA, and there would be 1 over HA or H naught A. So if we use this simple expression, we would be able to get QA and similarly QB. But the thing is that we are given HI as 5 watts per meter square Kelvin. So we know this first term in the denominator. We are given the thickness of the wall as 0.25 meters, and we know the thermal conductivity as well as 1, and we do not know H naught bar. So H naught bar is our unknown till now, and T infinity I is 20, T infinity outside is minus 20. So what we do not know in this expression is H naught A, or we could add. Okay, so in order to find out H naught bar, what we need to do is again follow the same procedure that we have been following in the previous problems, in the previous numericals. We could have written it in the form of HA delta T as we have been doing in the previous problems. But the thing is that if we write it as Q is equal to HA delta T, considering convection from this surface only. So the problem is that we do not know the temperature of this surface. So we would then be having two unknowns, one H naught or H naught bar, and then the temperature of this surface itself. So we would then be having two unknowns involved. So that is why we started with those temperatures or those temperature differences, or that temperature difference that is known to us. And since these are the two temperatures that have been provided to us, so this is why we are writing it in this particular form. Otherwise this problem could have been solved in the previous manner by considering convection heat transfer between this surrounding air and this surface, and this outside surface of the wall. But due to the involvement of two unknowns, we are writing it in this particular form of equation number 1. So coming back to our point, we have only one unknown, which is H naught bar. So now again the same procedure would be followed, means we will be able to calculate H from an expression of Nusselt number, and in order to have the correct expression of Nusselt number, we must know the type of the flow. Over here we already know the type of the flow, because we are told that the turbulent Mondelier conditions may be assumed over the entire wall. So we already know that the flow is turbulent in nature. So all we need to do is select that appropriate or most appropriate or the correct expression for the flow, for the turbulent flow over a flat plate. But we need to calculate the properties first. So we need to calculate the properties at the film temperature. So film temperature, this TF is in fact different from this TF. This TF means the temperature of the fluid inside the room. Over here this TF represents the film temperature, which is found out to which is calculated to determine the properties from the tables. So this would be the average of this Ts naught and T infinity. This Ts naught and T infinity, again the same problem that we do not know Ts naught. So we need to make an engineering guess over here. So as we can see that the outer air temperature, outside air temperature is minus 20. So we should be assuming a good value, a good enough value or a wise value of Ts naught. So We may assume it as minus 10, we may assume it as minus 5, that is fine, but it should not be taken as 10 or 15 degrees Celsius. We should not assume it as 10 or 15 degrees Celsius. There is a reason behind that. See, when the temperature over here is 20 degrees Celsius, right, and this wall is made of a very sort of insulative material. It is not conductive because it has a thermal conductivity of 1 only. So since this wall is having a very low value of thermal conductivity, there would be a large temperature drop when the heat would flow across this wall. There would be a large temperature drop when the heat will flow through this wall. So therefore, if the temperature over here is about 20 degrees Celsius, over here if it is about 20 degrees Celsius, so there would be a large temperature drop. So that is why we should not assume the temperature over here to be closer to 20 degrees Celsius. It should be far from 20 degrees Celsius. So you may take it as 0, you may take it as minus 5, you may take it as minus 10. So large values would not be a good engineering guess. We should go with small values because of a large temperature drop across this wall thickness. So I am taking it as minus 10, you may take it as minus 5 or you may take it as minus 15. There is no harm in it. We are only assuming it so that we can evaluate the fluid properties, and then we will validate whether our assumption was good enough or not. So we will get 258 Kelvin as the film temperature. So the properties will be evaluated at 258 Kelvin. Even if you assume it as minus 5, its average would be taken. So the difference would not be that large. It would only be of 2.5 Kelvin, and the properties will not vary by a large value if the temperature difference is only or if the temperature variation in our assumed value and the correct value is like or in any other assumption assumed value is just 2.5 Kelvin or 5 Kelvin, so it won't really make a difference. So that is why if you assume it as minus 10 or minus 5 or minus 15, things will not change by a significant value. So we will get the values of the viscosity, conductivity and Prandtl number as mentioned over here. Now we will calculate the value of Reynolds number. Although we know that the flow is turbulent, but we need to have the value of the Reynolds number because it will be used in the expression of the Nusselt number. So this is the expression of the Nusselt number. This is the expression of the Nusselt number or when the flow is turbulent over the entire plate, of course which requires the values of the Reynolds number and Prandtl number. So therefore we need to calculate the Reynolds number, although we already know that the flow is turbulent. So it would be again U times L over viscosity. So the length is 13 meters, velocity of the air is 7 meters per second, and this is the value of the viscosity. So we get this value as 54.8 exponent 5, which is less than the critical value of the Reynolds number. So we would not be concluding that the flow is turbulent because that is already known. We will only be putting this value of the Reynolds number in here, and we get the value of the average Nusselt number over the entire surface. Entire surface means the entire surface having the length of 13 meters. Means we are talking about room A right now. Right? We are not talking about room A and B combined. Rather, we are talking about room A right now because we have to find out QA. So the Nusselt number would be 8153, and upon equating it to HL over K, again it would be it would not be the local convective coefficient, rather it would be the average convective coefficient over the entire 13 meters length of room A. So that is why L is taken as 13 meters over here. So we get HA as 14.3. This is the value of the H bar between the outer surface of the room A and the outside air. So this is 14.387. So putting that value in here, because this was the only unknown, 1 over H naught A, this is the area, so we get this value as 3503 watts. This is the heat which is being transferred from room A to the ambient air. Now if we want to verify our assumption of Ts naught, so now if we put that Q in that if we use this Q is equal to HA delta T considering Ts naught, we were unable to use it before because we did not know Ts naught. So however we had to assume it anyhow, and we made a good engineering estimation. So Q is 3503. So now we will put this T as unknown, and we will try to see if we get a value close to our assumed value. So we get it as minus 14.6. So we had assumed it as minus 10, right? So if someone assumes it as minus 15, his calculations would be more accurate. But even then, even now, it really would not make any difference, because what is the difference between our assumed value and the value that we are getting? It is only 4.6. The difference is only 4.6. So when we will be taking the average for the calculation of TF, for the evaluation of properties, for the sake of evaluation of properties, this difference of will be divided by 2. So it would only remain 2.3 Kelvin. So the properties will not get changed by 2.3 Kelvin by a significant amount. So therefore our calculation is good enough. Now in order to find out QB will be found out in this manner. We cannot simply find out QB the manner in which we have found out QA. The reason is that the boundary layer will start forming. The reason is that the boundary layer will start forming from this end, right? So we cannot start for the calculation of room B just like we started the calculation for room A, because room A was the point where the formation of the boundary layer was being started from. So for room B we have to do the same, we have to follow the same procedure as we had followed in the previous problem, and you can see over here that QB would be QA plus B minus QA. So this is the same thing that we have performed in the previous problem. So now QA plus B would be H bar A times Ts naught minus T infinity, and now Ts naught is known as, you can put it as minus 14.648 from now on. So again, in order to find out QA plus B, what we do not know is H bar. So H bar would be evaluated using an expression of Nusselt number. So the expression of Nusselt number would remain the same, 0.037, because the flow is turbulent over the entire surface. So the same expression of Nusselt number would be used to find out the Nusselt number over here. However, Reynolds number will no more be this value, because this was calculated for 13 meters. So we need to, so when we sum up A and B, when we work for the combined length of A and B, it would be 13 and 7 means 20. So therefore therefore we need to calculate the new value of the Reynolds number and put in this expression. Prandtl number of course would remain the same, so we will get some value of Nusselt number, and equating that average value of the Nusselt number to HL over K, we will get H as 17.3. So this H is in fact the average value over the 20 meter lengths, over the 20 meter lengths, A and B combined. So then QA plus B would come out to be 5085 watts, and simply by taking the difference of QA plus B and QA, we will get QB of 1581 watts. So this is how the values would be calculated.